Hi everyone, my name is Audrey Watkins and my project is sensing and demultiplexing ultra-low frequency waves. I'm team ME68 and my faculty advisor is Dr. Osama Bilal. Ultra-low frequency waves are also commonly referred to as infrasound waves, and they are those with frequencies at or below 20 Hz. Infrasound waves often occur during earthquakes, volcanic eruptions, avalanches, and many other naturally occurring events, as you can see in the schematic on the right with the sources of infrasound. Infrasound waves have the possibility of causing extreme damage and harm to not only structures and buildings, but also to humans. They are oftentimes very difficult to detect as well. That is why understanding where, when, and why they occur can be helpful to those studying low-frequency waves in the different engineering disciplines. The objective of this project is to design and fabricate a tunable device that is capable of sensing these ultra-low frequency, or infrasound, waves with a size constraint of 30 centimeters. We begin by designing materials capable of sensing waves. To do this, we will be exploiting metamaterials, which are man-made materials that have wave propagation properties that are not naturally occurring. These metamaterials are made up of unit cells with certain dimensions and characteristics that change the material's behavior. As you can see here, we have a basic unit cell with dimensions A and B. Within the unit cell, we have these fixed magnets, which are the red dots, and we have the same magnets embedded within these floating disks, which we like to call the free magnets. By changing the dimensions of A and B, we can create different metamaterials. You can see on the left, we have metamaterial 1 with a unit cell of certain dimensions, and on the right, we have metamaterial 2 with a unit cell of slightly different dimensions. In theory, these metamaterials should have different wave propagation properties. We model the behavior of these numerically using the dispersion equation here, which takes into account the mass of the disk within the unit cell and the stiffnesses between the fixed and free magnets. Many people have studied metamaterials, but what makes ours unique is that we can reach the infrasound wave range by utilizing magnetic potential wells. By modifying the unit cell in 3 unique ways, we were able to create 3 unique metamaterials. We combine these into one T-shaped junction where each channel is considered its own metamaterial. Therefore, each channel is capable of sensing different infrasound frequencies. To experimentally test this, we excite the bottom channel at frequency f1 equals 1.1 Hz and f2 equals 2.4 Hz. Based on the metamaterials in each channel, the waves will propagate through either the left side or the right side. You can see this below in the frequency response function. At frequency f1 equals 1.1 Hz, the waves propagate through the bottom channel and are sensed in the upper left channel, but are not sensed in the upper right channel. However, when we excite the bottom channel at frequency f2, the waves propagate through the bottom channel and are sensed in the upper right channel, but are not sensed in the upper left channel. The propagation of the waves is tracked by the disk's oscillatory displacement within each channel. The numerical simulations that helped us model this device can be found in our published paper. Although our one-dimensional sensor did work, we wanted to create a two-dimensional sensor to give us a higher level of customization, or in other words, we wanted to have variable frequency ranges within the same system. This would allow for a broader range of applications. The main idea is to remove the fixed boundary magnets within the unit cell of the one-dimensional sensor, and instead use the crystalline structure formed within a self-assembled magnetic lattice as the new unit cells. In these 2 videos, we have a bike chain-like perimeter that we can move from a hexagon shape into a square shape, and we have 169 disks within the perimeter in both cases. These different shapes modify the local boundary interactions, therefore theoretically changing the wave propagation properties of the system. There are 4 main concepts in understanding the two-dimensional sensor idea. First, we change the outer boundary shape from a hexagon to a square. Second, due to the local interactions between the boundary magnets and the magnets embedded within the floating disks, the disks rearrange themselves, allowing for a new crystalline structure to emerge. Third, due to the newly formed crystalline structure, a new unit cell emerges as a completely different shape. And fourth, due to our knowledge about the effect of unit cell shape and dimensions on the metamaterial's wave propagation properties, the sensing ranges are modified. This leads to the conclusion that by changing the boundary shape of a metamaterial, its sensing capabilities are tuned. In summary, we've successfully designed and fabricated multiple devices that are capable of sensing infrasound waves. We created a one-dimensional sensor that we were able to model numerically as well as test experimentally, and we've also created a two-dimensional sensor that allows for a higher level of tunability and customization. This has also been tested experimentally. Both of our devices we fabricated are within our 30 centimeter size constraint as well. Our next steps are to incorporate electromagnets into the boundaries of the metamaterials, allowing us to change the properties of the system in time. We also plan to model this numerically to further understand how two-dimensional metamaterials behave.